The next speaker of the session is Peter Barker from UCL. Thank you, Peter.
Okay, so now something completely different. Thanks for the invitation to talk, and I'm glad that I could make it. After teaching yesterday, I've traveled overnight to come here, so if I'm a bit slow, please understand and get me to repeat it or something like that. So yes, I'm going to talk about experiments, and probably what I'm going to talk about fits in or sort of follows on a little bit from what Gavin Morley was talking about in terms of these experiments that he is working on that aims, and other people as well. I didn't hear the talk yesterday, so I don't quite know. So I've got this kind of boring title here. So hopefully, what I really want to talk about is, if you want to do these experiments, what I think is important and maybe not important as well. Because my research in general is optomechanics, particularly levitated optomechanical systems. So we now actually work with all three: magnetic levitation, this is what you might call electrical levitation or a Paul trap, but of larger particles. And this now is, this is really interesting because this is really quite a brand new quantum system, only 4 years old. And so, this represents, and this family of experiments, I think, will hopefully be interesting to you theorists as well, because I know there's a significant number of you. And so what I want to talk about really is my work in general, but in generally what I think is important for working towards, witnessing the quantumness of gravity. Because as Gavin said, these are really challenging experiments, and so I've been thinking about these experiments. Other people are actually working towards them, but I'd like to talk a little bit about that in the context of my own work. So okay, so just to kind of tell you what I do. So we have been working with these systems, these optomechanical systems, for a whole range of different topics, from very applied things, from looking at accelerometers to actually using these systems to characterize these particles, to really, we're now developing a system like this as a dark matter detector for a particular model of dark matter. And I'll finish off talking about those particular experiments. But most of the time I've spent really trying to control these systems, and that's what's required in these experiments, is to get very good control and to understand what your system is. And that's, we've come a long way to actually just demonstrating these things, to really understanding what these things are. But along the way, with Hendrik and others, we've been looking at wave function collapse, ways to make non-classical states that we talked about earlier. And as I said, just working out ways to control these systems. So, okay, so this is what Gavin was talking about this morning. So, this is the experiment that, there are many other ways, well, at least this part, to do this part, which is to create some sort of center of mass superposition. But of course, the real magic is, if you can create one of these, can you create two, and then get entanglement, and then really get some information on the quantumness of gravity. So I'm not going to talk about this other than, the fact that, as someone mentioned this morning, that if you need to control these systems, then, you need to control the center of mass motion of, for example, a diamond. And you saw Gavin's diamonds. They're kind of what I would call ugly structures, in that they don't have any, regular, simple geometric shape. But also, of course, the spin in them is stochastic. You don't know where it is. You have to spend a lot of time to even know that you have that spin. And on top of that, you need to actually orient this spin within a magnetic field. So you need to have that control, not over the center of mass motion, but also its angular degrees of freedom. And this is what I want to talk a little bit about as well. So, so first off, so this is really, so I can read it. I don't want to walk too far here. But this is a kind of a list, not a complete list, but a list of, probable requirements that you really need to do these experiments. So, it's clear that you need a very high vacuum. So, that's pretty obvious. You need to have fairly low temperatures. That's pretty obvious. But you also need to have low internal temperatures. So if you want to preserve, spin coherence times, then you need to have fairly low temperatures. And that's also what Gavin was talking about, that, ideally you'd like to operate these things at a Kelvin or so, or even lower. And so, some of the work that we've done is to actually refrigerate these particles while they're being levitated. And so levitation is a great thing. The reason why we levitate things is to isolate them from the environment. But of course, in isolating them from the environment, it means it's hard to do things like to take energy out, to cool them down. And so we've worked on laser refrigeration. I won't talk about that today, and that's capable of getting these particles down to 100 Kelvin, where normally they're in the order of 600 Kelvin, which is okay for some experiments and not for others. But I'm going to really talk about an idea, actually. So I'm going to talk about experiments that we've done, but also things that I'd like to do in terms of direct cooling using sympathetic cooling with cold atoms. I'll talk first off about this idea of coherent scattering in a cavity, which can be used to essentially cool all 6 degrees of freedom, and those 6 degrees of freedom are the 3 translational and 3 rotational orientational degrees of freedom. I then want to talk about sympathetic cooling, the possibility of doing sympathetic cooling, and explain why we'd want to do that. And so what's really important in doing these experiments is, particularly these experiments with micron-sized particles that are levitated, you can imagine you want to do an experiment, and you want to do an experiment over and over again. So you need to create a superposition, make a measurement, do it again, do it over again. So you need to work with something that you know what the mass is, what charge you have on the system, its internal temperature, its external temperature, and the shape and the material. So there's a whole list of things that you actually need to understand to do these, beyond a demonstration. To actually do something quantitative, you need to have a good knowledge of these things. So I'm going to talk a little bit about characterization and calibration. So let's start off with, so this just highlights basically, so this system is essentially, we use an optical field that essentially the electric field polarizes that particle, and that interacts with the electric field to hold this in all 3 dimensions. So we have essentially 3 translational degrees of freedom, but because almost any particle that we trap, so these are on the order of 100 nanometers to a micron in size, they generally are not spherical, so you have some shape here, and so this is where these other degrees of freedom come into play and need to be controlled. So how do we do that? Or how can we do that? Or what's one of the ways that we can do this? And I should say, this is just kind of from my perspective. Of course, there are other ways to do this. But I guess the general principles and the outcomes and the consequences of this method and others are similar. And so this is the experiments that were sort of spearheaded by Lucas Novotny and Marcus Aspelmeyer. We were working on these similar experiments, but the breakthrough here is to use an optical tweezers. So I just showed you an optical tweezers here, and you put that inside a cavity. And if this cavity is chosen to be resonant or near resonant with this field, then you can get a build-up of field in here. And so you have a directly scattered field and a field that is built up into the cavity, and you can get an interference between those 2 fields. And this interference field actually can be used to control or cool both the center of mass motion as well as the orientational degrees of freedom. So actually, it's quite a nice experiment, and you can have a single field that you can use to control all these degrees of freedom. And so if you were to sort of tilt the mechanical frequencies that you get, so if we're only talking about translation, you get 3 mechanical frequencies because there's 1 along the direction of this tweezer motion and 2 that are orthogonal to it. And so you can orient those fields and the light that they scatter into this cavity and have different orientations. And by controlling that orientation, you can control the interaction with the cavity, and thereby controlling the interaction, how well you can cool these things. And the general idea is essentially, so this cavity chooses the modes that can propagate in here, and essentially, in some ways, this is essentially just a filter that allows you to scatter blue shifted light, which takes energy away from these particles that are trapped in this optical tweezers. So this is our experiment that does this. So this all takes place in a block that's on the order of a cubic centimeter, where we can place these particles inside this small block here. We can illuminate it and create a tweezers with these lenses. We can actually see the single particle, and then we take a cavity on the order of, so it has a finesse of about 30,000. And we place these on the order of 100 nanometer particles inside this cavity and can trap them. And we can trap them, for weeks if all goes well. And so we can have a fairly well characterized particle that we can do experiments on. And so this is a typical particle that we would put in there. It's an electron microscope image of that particle. And so we have this particle in a cavity. We can look at the light that's scattered through the cavity, and we can measure the motion via a heterodyne system here, or we can look at the light that's scattered from the particle that's trapped by the optical tweezers, and we can look at rotation as well as translation as well. So we can look at all of these things simultaneously. So what does this experiment look like? So if I was just to take a time trace, for example, of, this is a sort of a homodyne measurement of the light that is being scattered from the particle. And if you look at this in the time series, you can measure a displacement and a function of time. And you can take essentially a Fourier transform of this SXX is the power spectral density. And the mean squared displacement is equal to the integration of that over the frequency. And so you can essentially, by finding the area under this power spectral density, you can determine an effective temperature. And so what you see here is two different translational modes. And what we're doing here is essentially removing the gas from the system. So as you pump air out of this system, the heating is being removed, and you're continually cooling, and essentially the area under this power spectral density decreases to the point that it either decreases down to the noise or just above the noise, so that you can make a measurement. And so, using this method, you can cool essentially the energy by a factor of 10 to the 7, and this is all at room temperature. And this is where the 0-point motion is on the order of 7 picometers. So, I guess the most recent innovation for us, and this is something that Marco Torres, who's sitting up the back, has been very involved in this, is to I've really talked about cooling the center of mass motion, but you can also cool essentially these orientational degrees of freedom, so rotation. So you can look at essentially rotation in alpha, beta, and gamma, so these 3 additional degrees of freedom. And again, you can use this cavity to do this. In this case now, if you're scattering light from this particle, it has different polarization components. And so those polarization components then populate this cavity, and they, by detuning these fields with respect to, or the tweezer field with respect to the cavity resonance, you can also do cavity cooling in this way to cool these down. And so this is another. So this is essentially a power spectral density of different detection mechanisms here that show us this alpha and beta rotational or orientational motion, X, Y, and Z. And so we can look at all of these simultaneously. The rotational degrees of freedom are interesting because actually it's a very nonlinear motion and they're strongly coupled. So it's a little bit, it's not just at least while these particles are hot. It's not just another simple harmonic oscillator, although it eventually becomes that way. So what we do with this cooling and how well this cooling occurs really depends on the shape of this system, and essentially by measuring. So if I go back here, I can look at these particular features. For example, we can look at this. This is the power spectral density of the displacement in X, Y, and Z. And looking at how those features are damped in low pressure gas, it tells you about the shape of these systems. And so what you can do is you can actually use this as a way to measure or characterize what these particles are. In fact, you need to characterize these to really have any hope of understanding how well you're cooling. And so for the plots that I've been showing you, this is the sizes of these. If you consider this particle approximating an ellipsoid, then we can determine the dimensions of the ellipsoid in each of those directions, and also a mass as well, based on several assumptions. So if we can hold these particles for a long period of time. So, we can hold them for, as I said, on times of seconds or on times of hours. And you can see the dynamics of how this power spectral density changes as a function of time. And if we're at modest vacuums here of 10 to the minus 5 millibar, you can see that X, Y, and Z are quite constant in frequency, but those interactions between this alpha and beta degrees of freedom that actually related to gamma, which is very difficult to see here. But eventually when you remove all the gas, or much more of the gas, so we're now moving down to a pressure of 10 to the minus 7 millibar, then essentially this process stops, this kind of nonlinear interaction between the gamma, alpha, and beta motion, and they separate out such that we can cool the alpha and beta and X, Y, and Z as well as probably gamma. And so this allows us to cool all of these degrees of freedom. So just as a summary to this is essentially a plot of the temperature of all of these 6 degrees of freedom. This last one, which is the gamma mode, is estimated from the dynamics of the system. But essentially you can see that we get down to the order of 100 microkelvin for some, up to millikelvin temperatures for these orientational degrees of freedom, which is so one issue here is that you can use this single cavity with these two orthogonally polarized fields to cool all of these degrees of freedom, but of course it's not optimum for any of these degrees of freedom. But the fact that we can actually control all of these degrees of freedom with a single cavity field means that it's quite powerful and quite useful for certain experiments. But maybe not for Gavin's experiment, and I'll explain that a little bit soon. So what I just wanted to highlight is that we can use these what we call motional spectra then to tell us the information on what particles we have. So for example, we've explored this in terms of geometrical shapes that we can get sort of inorganic materials, but also you can look at organic materials, and they all have different spectral features. And with some caveats, you can use this as a way of determining what you actually have if you want to do an experiment on these things. And this is just an example here of two different, this is yttrium lithium fluoride grown in two different ways. You can quite clearly see with these, there's very little dimensional difference between these two, but you can clearly see just by looking at this X, Y, Z and alpha beta motion here that you can differentiate between these species. Okay, so one of the important things that you might want to do, for example, with the experiment if I wanted to have an NV center, which is basically aligned within a magnetic field, you would like to know that you can control that orientation and then also determine what that orientation is. And so here's an experiment that we trap a particle in an optical tweezers, and then we can rotate, so as it's aligned in that field, we can rotate it around and look at the scattering from that and determine a particular shape. So, so let me just show you that. So this is an example here where we have these motional spectra for these nano dumbbells here. So we can look at X, Y, Z, alpha and beta here. But we can also see how well these fields are, these particles are aligned in the polarization of the field by essentially rotating the particle and looking at the scattered light. And so this, putting these two things together allows us to characterize these particles. Okay, so we can use this coherent scattering or optical feedback in these optical fields to certainly cool all of these degrees of freedom. And I've talked about coherent scattering, but you can also use feedback to do this. But of course, the problem, particularly with the experiment, this experiment where you might want to create a superposition of nanodiamond, using optical fields is usually precluded because essentially there's motional decoherence from the scattering of photons in these experiments. And so that really limits your ability to do experiments for any length of time. And so you really need to think of another way of cooling and controlling this motion. And so what I'd like to talk about now is a slightly more general way of doing that, using cold atoms. So you can imagine, so in the field of cold atoms, you can cool particles now down to, an ensemble of gas down to nanokelvin temperatures. And so the idea here is, can we combine cold atom physics with a trapped particle and use this as a very general way? So use collisions essentially between a cold gas with a trapped particle, which that can cool all of these degrees of freedom, but also can potentially cool the internal degrees of freedom as well. And so the general idea here is that you take, so if I move back one, you take an optical field and you essentially produce 3 beams that overlap with your particle, and the result of this is that you can create essentially this symmetric field. So this is so if this light is red detuned with respect to a resonance, then it attracts these particles towards this this nanoparticle, which is not particularly attractive because essentially, because these are typically hot, as the particle collides, it's going to release energy and actually heat these things up. But if I can choose my light field so that I tune it to the blue of a transition, then you can actually repel atoms that are coming towards this. So if I've surrounded this with a gas, and this light is blue detuned with respect to this, these atoms, for example, cesium or metastable helium in this case, then I can create a repulsive potential. And it's an interesting repulsive potential because it's essentially a Coulomb potential. So the range of this potential is quite large. So it's much larger than the size of the particle, and so you have a huge cross section here. And so this is the idea I can choose. So this is experiments in metastable helium. This is a common transition that's used in metastable helium, and I can work to the red or blue of this transition and either attract these atoms to my levitated particle or I can repel them. And so why is that interesting? So if I can essentially increase the cross section and repel these particles, then it means I can actually interact with it. So I can cool these particles via sympathetic cooling. So the idea here is that the collisions are completely inelastic, and so it leads towards a cooling in this particular case. So you could look at this, as I said, the cross-section is actually 6 orders of magnitude larger than the physical cross-section. And because of this, actually I can get cooling rates that are comparative to what you can do with regular cooling using the coherent scattering technique that I showed you before. The difference here is it doesn't require anywhere near as much as light, and it's less likely to heat the particle. So what else can I do with this sort of potential? So you can, well, before I describe that, what I can do then is I can trap one of these particles, for example, in a pole trap that we have, and I can surround it with a whole lot of cold atoms, and I have blue detuned light from the resonance here. And I can get cooling rates on the order of 10 kilohertz, which is comparable to what the cooling rates that I can get with cavity cooling. And really the only significant heat or heating or decoherence in this system is whatever charges that I have on this and fluctuating charges. And this is a sort of a typical thing that you would have in a pole trap with atomic ions. And so really it seems feasible that you could get temperatures in all degrees of freedom on the order of 10 microkelvin by collisions, essentially, with these cold atoms. And so this is something that we haven't done, but we would like to do, because the beauty of this is that, for example, if you wanted to perform an experiment where you're creating a superposition, I can be cooling this and then turn off these laser beams, and the cold gas disappears, and I'm left with a particle that I can then work with to do experiments. So what else can you do in this system? So if I have a red and a blue detuned field, I can create both an attractive potential and a repulsive potential. And so you can essentially create a potential that, so if I can create an optically repulsive and attractive potential and include this with, of course, there's going to be a Casimir-Polder interaction with the atoms next to the surface. But essentially what I can do is create a sort of an atom nanosphere molecular system. And so I can have these bound states, but it also means that I can essentially trap a particle very close to this nanosphere. So it means I can have a sort of this large macroscopic thing with a nice quantum system right next to it. And this is attractive to me because when you have embedded atomic systems such as NV centers, they're often broadened by phonons, essentially. And so this really affects, your ability to manipulate the lifetime, the general T1 lifetime, but also spin coherence lifetime. And so to me, this is kind of an attractive system to explore because we already have a lot of control over atomic systems. For example, I'm talking about metastable helium here, but it could be cesium. It could be any of these species that now we have fantastic control over. And these are systems that are very clean. The only thing that's not clean about this system, of course, is that there is unlike impurity that's embedded in diamond, which is rigidly embedded. Of course, this is on a spring, right? So it's moving. But in terms of you have frequency here on the order of sort of vibrational frequencies between these two masses on the order of 100 kilohertz to a megahertz, compared to motional frequencies that are on the order of probably 10 kilohertz to 1 kilohertz. So in some case, this is quite a rigid system, and it'll probably adiabatically follow the center of mass motion. So to me, this is an interesting system to work with because it's potentially quite clean, and we know the physics of how to trap these particles around these systems. And just as a side note, I mean, if you're interested in scattering, of course you can look at the nature of the quantum nature of this by basically just directing atoms at this surface. And of course, because you get all these scattering resonances as you mind you, at very low energies, but you can see these scattering resonances, which shows the the presence of these vibrational states. So, so I think this is an interesting system, and of course, what you can then do is consider then, well, I mean, if this is like an NV center, can I just do a similar experiment? For example, can I trap this system in a trap like this? This is actually a different experiment that Marco really spearheaded. Well, it's not an experiment, it's a thought experiment to create atom nanoparticle superpositions in a little bit different to what I'm talking about here, but using essentially this optical field to support an atom or associate an atom with this surface, and then manipulate the motion of the larger particle by manipulating the spin in the atom. And so I recommend that. But of course, with the system that I've shown you as well, you can consider doing an experiment very similar to this NV center experiment, but instead using this atom as your impurity. Okay, so just to comment on this, so this is kind of what I would say, it's an interesting hybrid quantum system. It's tunable because you can essentially, if you have embedded impurity such as such as NV in diamond, you can't really control that so well. Whereas here, using these optical fields, you can control the type of potential that you're trapping in. So you can control trapping frequencies. You can put in different species. You can use it for sympathetically cooling the system before you then actually associate a single atom with these bound, with these trapped nanoparticles. And so this is interesting because we don't require the very high intensities that you require, for example, for the experiments that I was showing you before with coherent scattering. The only system that we know is more or less a quantum system. And lastly, potentially you can cool both the internal degrees of freedom as well as the rotational motion and translation just by this very general method of sympathetic cooling. And so in my opinion, it's kind of an interesting thing that I would really like to explore in future from an experimental perspective. Okay, so I've got plenty of time, do I? Yeah. So this is I guess, this is slightly less along the lines of witnessing the quantum aspects of gravity, but it's sort of most recent work, so I thought I'd show it to you. So what we're interested in doing is measuring small impulsive forces using these levitated particles. So, so here, there's our typical system here. In this case, it's surrounded by electrodes, and these, we can arrange to either have these nanoparticles on the order of 100 nanometers, they can be charged. And so we can use external electrodes to manipulate the motion, so we can use it as a way to cool. We can measure its motion and then apply feedback that opposes that, and cool these particles again down to the order of, on the order of 100 microkelvin. But what we'd like to do is, this is a fairly light system. We have very good displacement sensitivity, and therefore very good force sensitivity. And what we're interested in doing is essentially measuring, using this as a sensor to measure collisions, for example. And one of the projects that we have is to really look at a particular dark matter model, composite dark matter, and to make measurements. And Dave Moore has already made measurements with larger particles, but the aim here is to use these much smaller nanospheres, which have a higher force sensitivity. But, you can look at things with collisions with molecules, photons, neutrons, and dark matter. So it's a sort of very general thing, and I want to sort of treat it really that way, as a general way of looking at these collisions. So, so in our particular case, I mean, we're looking at using these optomechanical systems to really test a range of dark matter models, which I won't go into. I just really wanted to say that this particular experiment is really looking at this composite dark matter, which what we're looking at is collisions, effectively. Oops. Sorry. So yeah, so what we're looking at here is this composite. So this is basically it's a fermionic or bosonic dark matter particle coupling to this particular scalar mediator, and this leads to this sort of formation of these bound dark matter nuggets, and it's a particular model of many different models that you could test with optomechanical systems. But the important thing is that it has this interaction. It's essentially like a Yukawa potential. So what we're looking at is essentially an interaction of this particle with the nucleons in this system. And if you were to look at this particular experiment, you should expect essentially as this nugget moves along that it should collide with this particle, and that we would measure a displacement or a force when this interaction occurs. And so we've started doing experiments along this line to measure this. So you might ask, well, so this is a nanoparticle. It's a very small system. You know, how is that useful for detecting dark matter? Particularly, you know, when you have these larger detectors, which are essentially, you know, 10 tons of xenon looking for WIMPs. You know, what can you do with a small system like this? And well, there's two answers to that. One is, of course, you can have an arrays of these particles, but the total mass is still small. But what's really important here is that you get the directionality. So with these systems, you know, we have X, Y, and Z. So we can measure forces in X, Y, and Z, and we can essentially give a direction if there is and there should be a preferred direction to essentially dark matter events as we essentially traveling through, we're going around the sun, but also traveling around the galaxy, and that, you know, that dark matter wind is on the order of, you know, 200 kilometers per second. And so if you were to look at displacement in different axes, you might expect that this is an oscillator, you give it a kick, and then it would ring down after some period of time. So, so as I said, so Dave Moore, who I think is speaking tomorrow or has already spoken, they have already made a search with larger optically levitated sensors and put some initial limits on this using their sensors. And here they have particles on the order of 10, 20 microns, optically trapped, and it's surrounded by electrodes here, so they can calibrate the motion that they get. And so our aim really is to do this for much smaller particles, and we've started doing this. And so the idea is that you trap a nanoparticle, you characterize the nanoparticle because you need to know what the force is or the impulse that you're giving it, and then you essentially monitor this nanoparticle position for weeks at a time, and then you need to process that event. And so this is the particular experiment. So we have a tweezers here. There's electrodes that allow us to cool it and also apply pulses, and then we can detect X, Y, Z and rotation as well. So very similar to the experiment that I was showing you before. And that's what the experiment used to look like. And then we can basically take the pressure down, and we're then less sensitive to collisions with molecules and various things, and get to temperatures on the order of 100 microkelvin, which we don't need to be in the ground state to do these experiments. What's more important is that we have good detection sensitivity. And so what's interesting about this is that this whole problem has really been, the physics of this was really explored with these original Weber bars, these gravitational wave detectors, because they're somewhat larger masses, but we're looking for an impulsive kick on these detectors. And so a lot of the machinery needed to do the analysis has already done for us. And so we essentially, we're looking for a signal. In their case, they were looking for gravitational, like strain, essentially from a gravitational wave. And what we're looking for an impulsive kick in the presence of white noise, and we need to filter that out. And so this is that process. So these are the three frequencies that we're looking at, and we're looking for impulsive events in here. And so what you see here, these are kicks that we've given to calibrate this process. You can see kicks as a function of time, and the filtering gives us this impulsive event, so we can see these impulsive events. And actually, if the noise is low enough, then we can see not only the impulsive event that we're looking for, but we see essentially the ultimate noise limit that's determined by either collisions with the background gas, which will always exist even at the lowest vacuum, but of course with the photons that we have. So, you know, with the right sensitivity, we can see that. And I'm really running out of time. I've got 30 seconds left, so let me finish. So we've done these experiments and calibrated these things, but I also wanted to show you that in order to really do these experiments, we've been putting radioactive, we wanted to see interactions with radioactive particles, and what you see here that I'll show you is interactions with alpha particles placed below these levitated nanoparticles. And so you can in principle see a kick, but you also see a charge change. And so we continually, we run experiments for 40 days, and we can see essentially every 8 days we get an interaction. So this is I guess this is the point, is that we have a radioactive source underneath this, but because these particles are so small, the cross section is so small that we see an event every 8 days from these collisions, and you can see the resultant charge change, which is stable for some period of time until you get another kick. So I just wanted to finish off with that. I'm sort of running a bit. So what I sort of have tried to say is that I wanted to give you a review of some useful techniques that may be useful for future experiments that are looking at the quantumness of gravity. I wanted to show you that, you know, we are increasingly getting a lot of control over all of these degrees of freedom, which is needed for these experiments. And by sort of studying the motion in these traps, we can really characterize the particles, you know, the charge, the mass, all of these things which are important for really, before you can really begin to do these experiments, these quite complicated experiments that are creating, they're looking at entanglement between these two center of mass superpositions. So we'll stop now, and thanks for your attention.
So we have time for a few questions.
Okay, nice talk. I think I lost the part, why do you expect kicks from dark matter if the system is probably not able to feel kicks from neutrinos coming from the sun, which are zillions of neutrinos coming from the sun, and the interaction is as weak as, of dark matter, is as weak as the interaction from neutrinos?
Well, I mean, we would love to be able to see neutrinos from the sun, but we certainly don't have that sensitivity. I mean, that's a long way off to be able to see, you know, either, you know, neutrinos and neutrons. I mean, you know, we just don't have that sensitivity at the moment.
So the question is, why do you expect to see dark matter? Because you have more neutrinos, and neutrinos dark matter interaction is weak, and or even weaker than neutrinos.
Well, I mean that's the whole point, right? The model, and I'm not an expert on that particular model, and really all we can do is put limits on that model. But I mean, I guess some people have the expectation that we might be able to see something there. So, you know, I mean, essentially we're in the game of essentially putting limits that are better limits than other people, and it turns out that optomechanical systems are actually, you know, very competitive over a wide range of dark matter masses. And so that particular experiment I just showed you was this particular, you know, composite dark matter model, but you know, there are a whole range of others that optomechanics, through this, you know, through this sensitivity, but particularly this directionality that's really important that you don't get from, you know, WIMP searches and things like that. You know, that's just not the directionality. So I think optomechanical sensors are promising.
Thanks for the talk. So you said you're testing a specific dark matter candidate. I mean, I got a bit lost on what the specific model it is. I mean, can you explain to me that?
Well, I'm not an expert in it, so I can't explain it too much. But I mean, essentially, I mean, you know, so there's this. If I go back here. So, I mean, you're essentially looking at this formation of these nuggets of dark matter, which, you know, I can't tell you too much, but essentially where this particle essentially has this Yukawa type potential. So this leads to this interaction between the nucleons leads to this Yukawa type potential, which that's what we can test, essentially. We can test that collision, so we can look for these collisions and put limits on what these interactions are. So what this GN is here, for example. You know, we know the number of nucleons, so we know a lot about our system, but essentially you're just putting limits on this and of course the dark matter mass. But beyond that,
so it seems that you're testing some sort of a class of.
Yes.
Yeah. Okay.
Yeah.
It's not a super specific candidate, but a class of candidates. Yeah?
It's a class of
Okay.
candidates,
Okay.
yeah.
Okay. Thank you.
One more question. Yes, sure.
Hi, Peter. Thank you for the wonderful talk.
You're welcome.
I was just wondering, like, with your optical refrigeration, how low could you go and how low in temperature have you gone?
Sorry, can you speak a bit louder?
So with the optical refrigeration,
Yes.
I was wondering, like, how low have you gone up until now?
We've gone to about 120 Kelvin,
Okay.
so not very cold.
Mhm.
And I mean, theoretically, it's limited by about 60 Kelvin.
I see.
So you can't go low. But of course, these levitated particles that we have are probably about 600 Kelvin.
Mhm.
So it's
Right.
significantly cooler, but not as low as you would like it to be.
How low would you want them to be to do the experiment, like the entanglement experiment?
Well, you know, depending on the type of experiment. So,
Mhm.
I mean, this is kind of why I'm interested in, you know, associating an atom with
Right.
these particles, because they probably don't need to be any lower than room temperature.
Mhm.
But of course, you know, in all of these experiments, we would like to be at a Kelvin or even lower, you know, so you would get increased, you know, spin coherence times, increased motional decoherence, you know, so the lower the better, basically.
Okay, thank you.
Okay. Okay, Andrew, you can speak.
Yeah, hi, really nice talk, Peter. So I had a question about the sympathetic cooling.
Yeah.
So with cold atoms, you normally have to have a very good UHV, you know, baked environment and things like
Yeah,
that. And so
yeah.
with the nanoparticles, oftentimes they're loading from relatively large pressures. And so have you thought about how to combine those systems in a way?
Yeah, I mean, we
With
already load, you know, in one of our experiments, we already load in a dry manner with this, you know, Liad technique. So, yeah, I mean, you can't load the way many of us do. It has to be a much cleaner way of loading. So I don't really see that as being, you know, a particular problem. And certainly, you know, because we can hold these particles for, you know, in the Paul trap for, you know, 3 months easily. You know, having to wait a week for the thing to pump down is not really the end of the world, I don't think.
Nice, yeah, thanks.
Okay, so let's thank the speakers again. Now it's